Hello everyone, my name is Sinuo Liu. I am a joint PhD student in University of Science and Technology Beijing and Carnegie Mellon University. Today, I will present for the paper Multiple Scale Simulation Method for Liquid with Trapped Air under Particle-Based Framework. So, what are we doing? We are adding air materials to fluid, especially liquid. Exciting fluid simulation method is able to describe the motion of fluid realistically, which puts higher requirements on the detailed simulation. However, the physical description of air materials is extremely complex, which makes it difficult to simulate them realistically. In this video, a dolphin drops into the sea and makes some turbulence. After adding materials such as bubbles and foams, the visual effect is enhanced. The fluid is simulated by a classical particle-based method, SPH method, which is short for smooth particle hydrodynamics. Fluid is composed of thousands of moving fluid particles that are represented by pink spheres. The air materials are also present by particles and are added to the simulation by a post-processing scheme. In this figure, all particles are represented by white spheres. In terms of generation of air material, it can be divided into three categories according to the mechanism: trapped air, nucleation, and boiling. First, when moving intensely or rushing quickly, air will be trapped in fluid, such as pouring water into a glass. Second, when environment such as temperature and pressure changed, air that originally dissolved in water may precipitate to generate nucleation bubbles, like foam in beers. Third, when the liquid is heated above its boiling point, surface and internal fluid particles vaporize simultaneously, like bubbles in hot water. In this paper, we focus on trapped air in liquid. The study of trapped air is mainly divided into two types according to the size of air materials. When modeling the large-size air material, the fluid is usually regarded as air-liquid two-phase fluid, and a complex physical model will be established. This type of model are able to describe the shape change of bubbles vividly, but the calculation process is very time-consuming. Besides, the mass transfer process between air particles is not well described. As for the simulation of small-size air materials, the shape and the size of particles is usually ignored, and only the microscopic motion is described. Generally, this type of model is a post-processing model which can enhance visual effect with negligible computational overhead. Besides, without Brownian motion, large number of air particles will move with similar patterns and result in a periodic distribution. In real life, air bubbles of different sizes are usually generated at the same time. Simulating different scales of air materials simultaneously in a unified framework can achieve a more realistic result. Therefore, we propose a unified multiple-scale air material simulation method for particle-based fluid. For large-size air material, the mass transfer phenomenon is described based on the inverse diffusion equation, and the interaction scheme is improved using a new high-order kernel function. For small-size air material, we improved the velocity update function to get a better result, and the Brownian motion is added to solve the periodic distribution problem. Next, I will illustrate our method in detail. The quantity of air material is generated by each fluid particle is based on the velocity difference and the kinetic energy. With a maximum sampling rate, we can obtain the number of new generated air particles. Next, we draw a cylinder based on the trajectory of the fluid particle and randomly initialize the air particles in this area. Since the cylinder is really small, air particles tend to form a cluster under this scheme. To solve this problem, we set the size of the generation area, the cylinder, to be adjustable, which means it will become more larger. Then, the air particles are divided into 6 steps based on the size and coupling degree with fluid, as shown in Table 1. In physics, bubble's radius in a liquid obeys a log-normal distribution. A random number obeying a log-normal distribution is used to determine the initial radius of air particles. A controllable parameter is introduced as a threshold for dividing the size of the air particles. When the radius is larger than this threshold, the air particles are regarded as large-size air material, while the other will be regarded as small-size air material, and the radius of small-size air particle is valued as E. This is an injecting water experiment with 29,000 fluid particles. A is the real sense. B, C, and D are the simulation result with particle results on the left and the rendered result on the right. In particle result, small-size air material and large-size air material are marked as red dot and blue sphere respectively. By adjusting the control parameter, the occupation of large air particle is changed, and different styles are realized. Both large-size and small-size air particles are classified by the coupling degree with fluid. Subfigure B shows the rendered result of air materials generated by blocks falling into water. The marked result is shown in subfigure C, where spray particle, foam particle, and bubble particle are marked by light blue, green, and red respectively. Third, air particles are dynamic surviving particles. Small air particles with lower surface energy are more stable. So, in each time step, we randomly remove the air particle based on their age and radius. The probability that an air particle is deleted is controlled by this function. In this paper, 2 dynamics models are established for different sizes of air material. The small-size air particle move under the gravity, the buoyancy, and the coupling force with fluid, while the large-size air particle will also coupling with neighbor air particles and solid particles. As shown in this figure, in each time step, the velocity of the air is calculated together by the velocity variation caused by the gravity, the buoyancy, and the drag force of the neighboring fluid particle. The value of the coupling parameter depends on the degree of coupling. We also implement Brownian motion. 2 neighbor air particles have similar fluid neighbors. The motion of air particle depends to a large extent on the average velocity of its neighboring fluid particles. Therefore, if Brownian motion is not added, regular periodic distribution of air material will be observed. The slack function is used to describe the velocity offset angle of each small bubble particles. The probability of air particle to move following the Brownian motion is determined by the degree of choice of this area. This is a tiled water injection experiment with 20,000 particles. In order to see the effect of Brownian motion more clearly, only the small-size air particles are rendered. By adjusting the parameter kappa, the motion freedom degree of air material changes. The value of kappa in subfigure B, C, and D is 1, 0.8, and 0.6, respectively. When kappa equals to 1, Brownian motion is not added, and the distribution of air material is periodic. After adding Brownian motion, the visual effect is improved. The dynamics model of large-size air material is slightly different to small-size air material. Due to the large volume, their coupling degree with rigid body and the neighbor air material is relatively high. Therefore, in addition to the gravity and the coupling force with fluid, the interaction with rigid body and the air material are also need to be described. Air particles that are not in plateau equilibrium are unstable and will quickly be rearranged under surface tension. The plateau equilibrium distance of 2 air particles is shown on the screen, where lambda is set based on the coupling degree. We use a new high-order kernel function to deal with the interaction between two large air particles. The peak value of our function is a finite value, thereby avoiding the explosion phenomenon. We use a pattern similar to air coupling to describe the coupling force between solid particle and air particle, where the control parameter takes the different values. According to Laplace-Young's law, pressure of small particle is larger than that of the larger bubbles. When two bubbles contact each other, the smaller one tends to press the internal air into the larger one. Therefore, we describe the process of mass transfer using an inverse diffusion equation. The discretest mass transfer formula is shown on the screen. Besides, only two large bubbles with a relative larger volume difference will transfer air between each other, and the theoretical value is 0.8. This is to avoid air transfer between all bubbles, resulting in a rapid reduce of large air materials. Our method tends to generate air particles in fast-moving areas, and the one-way coupling scheme makes it more suitable for efficient real-time simulation rather than high-accuracy simulation. In terms of dilation scheme, although we set the large-size air particle with larger surface energy to be more easier to be dilated, some large-size spray particles still have a long lifetime. These surviving air particles will be able to jump out of the liquid surface, affecting the visual effect of animation. This issue could potentially be resolved by using a smaller buoyancy parameter to reduce the velocity of these particles as they approach the surface. Fully optimization of this problem will be our future research work. We also plan to combine our method with some turbulence simulation method to further enhance the visual effect. This is the end of our presentation. If you have any questions, please feel free to contact us. Thank you very much for your attention.